In the previous lecture, we have discussed the variety of data that is available in the statistical sciences, and we saw that we can represent it graphically to make it appropriate for analysis or for understanding the kind of data that we are having, what does it represent, etc. However, only graphical or tabular representation may not yield too much. One may have to present it in a very systematic way, so that one can draw various characteristics of that population or that data. So, we will look at how to consider the frequency distribution of the data. The first thing that we observe is that in what way the data may arise. So, the data may arise in one of the two possible ways. One way could be that to start with the data is numerical. For example, if we are writing down, say, incomes of families in a town, okay. So, in that case, corresponding to each family, you are writing down certain numerical value. Suppose we are recording the incomes per month. So, the incomes could be, say, 12,000 rupees per month, it could be 2,500 rupees per month, or it could be 1 lakh rupees per month, etc. So, here the primary recording of the data itself is in the numerical form. This data is said to be variable data or frequency variable data. So, we can give a nomenclature here like 12,000 we can write as x1 value, 2,500 we can write as x2 value, 1 lakh as we can write as x3 value, and so on. So, the data is recorded in the form of variables x1, x2, x3, xn. These are called quantitative variables, because corresponding to each variable we are having a numerical value associated with this. So, this is termed as quantitative data or quantitative variables. But there are certain other places where the data is not recorded in the beginning as a numerical data. For example, if a manufacturing process is on and certain items are being produced, a quality control inspector, he measures certain characteristic of that product. For example, if these are, say, bolts produced by a manufacturing process, so they measure the diameters of the bolts, and if the bolts are having diameter less than a certain value or more than a certain value, then they are considered to be defective, and if the diameters are within a certain range, we call them to be all right. For example, if the average diameter is, say, 3 mm, and we may specify the limits as 3 plus minus 0.01 mm. So, if a bolt produced has a diameter between 2.99 mm to 3.01 mm, it is considered to be all right, otherwise it is said to be defective. However, the inspector reports an item to be defective or non-defective. So, corresponding to each item, the value recorded is either D or N. Now, if we record for 1000 bolts D or N, then out of this maybe 50 are defective and 950 are non-defective. So, at a second stage the data becomes quantitative. This is known as attribute data, because here the initial recording is in terms of the character, that is, or you can say the type. For example, if we are looking at a population of students, and we may then classify them as in the school students or a college student. So, each student may be a school student or a college student. So, if we have, say, 10,000 students, then out of this 10,000 maybe you have 7,000 as school students and 3,000 as college students. So, whenever we classify the data according to certain property, then it is said to be attribute data. It is the techniques for analysis of attribute data and the quantitative data are somewhat different. In this particular section, we will explain how to make frequency distributions for the quantitative data. In the case of attribute data, it is relatively easy to make a frequency distribution. For example, one may have two characteristics according to which we classify the data. Suppose we look at a set of, say, inhabitants of a locality. Now, when we do the survey, we may record their gender, that means male or female. We may also record whether they are graduates or non-graduates, that means below graduates. So, now suppose we have a population of 10,000 in that locality. We may classify firstly according to male female. So, maybe we have 4,500 males and 5,500 females. Now, among this we look at how many graduates and non-graduates. So, suppose the number of graduates is 3,000 and there is 7,000 non-graduates are there. Now, out of the 3,000 graduates, how many of them are males and how many of them are females? Suppose it is 1,500 males, 1,500 females. Out of 7,000 non-graduates, how many of the males? So, 3,000 are males and 4,000 are females. So, this is known as contingency table. So, an attribute data can be represented in the form of a contingency table. Here we are classifying according to two characteristics. One may classify according to 3, 4, etc., and accordingly the representations can be made in the form of contingency tables. Now, we consider variable data. Suppose the data is recorded on the number of peas in certain pea pods, pea pods. So, in each pea pod, how many peas will be there? So, there may be no peas, there may be 1 pea, 2 peas and so on. So, finally, we classify. If it is 0, we neglect it. Out of 198, how many are having 1, how many are having 2, how many are having 3, how many are having 4, how many are having 5, how many are having 6 and how many are having 7 peas. So, the primary data would be in the form of certain numbers, like we take 1 pea pod and see how many peas are there, say 3. Then we take another one, how many are there, say 3. Next, how many are there, suppose we say 5. Next, how many are there, suppose we say 6. Next, how many are there, suppose we again have 3. So, we record the data. Now, from here we make the frequency distribution. Now, there are certain elementary techniques for creating the frequency distribution, that is called counting techniques. So, if 1 occurs once, we make a tally mark. If 2 occurs once, we mark a tally mark. Suppose 4 occurs, we make a tally mark. Suppose next 1 is again observed, we make a tally mark. Then suppose next 6 is observed, we make a tally mark. Suppose then next 5 is observed, we make a tally mark. Suppose again 1 is observed, we make a tally mark. Next, suppose 4 is observed, we make a tally mark. Next, suppose 1 is made. Suppose we have 5. Suppose we have 3. Now, suppose 1 is again observed, then these are already 4 symbols, we cross it. this is showing a block of 5 frequencies. So, in this elementary way one can make a distribution and see how many frequencies have occurred for each of them. So, suppose if I have observed only this much, we can consider the frequency distribution as corresponding to 1 it is 10, corresponding to 2 it is 7, corresponding to 3 it is 1, corresponding to 4 it is 2, corresponding to 5 it is 2, corresponding to 6 it is 1, corresponding to 7 it is 0. So, if I have taken only these many p pods, so this is 23, out of 23 p pods, the frequency distribution of the number of the p's is given by this. Let me take a rather detailed example where 198 p pods were recorded corresponding to their number of p's per p pod, and the frequency distribution turns out to be, so we write here number of p's and here we write frequency, that is how many times each occurrence is there. So, 1 is occurring 4 times, 2 is occurring 33 times, 3 is occurring say 76 times, 4 is occurring 50 times, 5 is occurring 26 times, 6 is occurring 8 times and 7 is occurring once. So, this total sum is 198. This is called basic frequency distribution. Now, one may present this data in various forms. One may look at relative frequencies here. By relative frequency we mean the percentages or the proportion of each number in the total. So, for example, how much is 4 of 198? It is nearly 0.0202. How much is 33? It is 0.1667. 76 is 0.3838. 50 is 0.2525. 26 is 0.1313. 8 is 0.0404. 1 is 0.0051. The sum is 1. If we look at the last column, it tells the relative occurrence of each number in the sample. For example, 3 occurs nearly 38% times. Say 2 occurs nearly 16.6% of the times. 4 occurs nearly 25% of the time, whereas 1 or 7 they occur very less. So, 1 occurs only 2% and 7 occurs only 0.5% of the times. So, this information is also useful. Sometimes we look at cumulative frequencies. Cumulative frequencies. When the data is arranged in a tabular form and we have the frequencies, we may add them successively. So, for example, here it is 4, then 37, then 113, then 163, then 189, 197, 198. If we look at this cumulative frequency, it tells how the frequencies are adding up. So, this also gives lot of useful information. This type of representation is called a discrete table or discrete variable table, because here corresponding to each value certain values are given. However, sometimes the data is too numerous. For example, if we are recording the heights of students or incomes of the families, then the data is too numerous, in the sense that if we record heights, we are not only going to record it in terms of inches, it may be in the terms of the fractions of inches or centimeters, and then the fractions of the centimeters and the fractions thereof. So, the total number of values that we are considering are too many. This is called continuous data, and in that case it is more appropriate to split the data into intervals. For example, we may consider how many persons are having height from 140 centimeter to 150 centimeter, how many of them are having height from 150 centimeter to 160 centimeter, how many of them are falling into 160 to 170 centimeters, etc. So, this type of classified data, once again, if we have the raw data, so raw data will be of the form, say, I will just give few values here. The heights are recorded in centimeters of, say, Indian males. So, the heights may be in the form 169 centimeter, 166.7 centimeters, 159.9 centimeters, 157.8 centimeter, 169.9 centimeter, and so on. So, now from here we make classes. Now, we may make classes of various kinds. We may make from, say, we may record what is the lowest value and what is the highest value. Suppose the lowest value is, say, 144.6 and the highest value is, say, 184.5. Then we look at this difference. The difference is 39.9. Now, this is not a very convenient number. However, if we are very strict, we can look at only this difference and divide it into, say, 6 classes or 5 classes. Now, if I divide it into, say, 10 classes, then each class will be of the length 3.99 centimeter. That means my class intervals will be like 144.60 to 148.59 and so on. Now, this looks slightly inconvenient from mathematical point of view. So, a better option could be that I can consider the length from 144 to 185, or even better we can consider something like 140 to 190, which is a more convenient representation. So, this is the total length is 50 centimeter, and if we divide into intervals of length, say 10 intervals, then the interval length will be like 140 to 145, 145 to 150, 150 to 155, 155 to 160, 160 to 165, 165 to 170, 170 to 175, 175 to 180, 185 to 180 to 185, 185 to 190, and that is all. And in the next column, we will put the number of people occurring in each. So, the numbers may be like, say, 30, say 35, 60, 65, maybe say 62, 70, 75, maybe again 70, 62, 51, etc. Again, here we may consider frequency as well as relative frequencies. Now, when we present this class intervals like this, the rules for the counting have to be made. For example, 145 is here, 145 is here. So, we have to make a rule that this will be considered less than or equal to. That means, if a person is having height equal to 145, then he will be considered in the preceding class. Or we may make a rule of the reverse side, that is, if it is 145, he will be considered in this class. But we have to make a rule prior to preparing the table. Then next thing is the number of the class intervals. How many class intervals are sufficient to represent a given data into a frequency distribution? So, the general principle is that the number of intervals should not be too small, it should not be too large also. If you keep too small, then lot of information is hidden. For example, if I make the intervals only, say, 2 intervals, say 145 to say 165 and 165 to 190. Then we are not able to distinguish the persons who are say between 140 to 150 and between 150 to 160, etc., because everything we are putting into the same. At the same time, if we are making too many intervals, suppose in place of 10 I make here 25 intervals of length 2 each. So 140 to 142, 142 to 144. Then it will be difficult to analyze. It is same thing like in the discrete case, that if I have too many values here, then it is not easy to handle that value from a statistical methodology point of view. There are some guidelines for making the class intervals and the number of intervals, and one should follow them before making the thing. Now, the next thing is the graphical representation of frequency distribution. So, if we have a frequency distribution of this nature, then we may simply make a bar diagram in the form. So, on the x axis I plot this number. So, 1, say 1, 2, 3, 4, 5, 6 and 7, and we make a bar of the height which is the equivalent to the frequency given here. So, now we have to see the relative position. So, if I have this as say 5, then 10. So, now you see that I need a large gap here. So, this is 20, then this is 40, then this is say 60, then this is 80, and so the table has to be very large. So, in place of this I can make this as 10 say, then this is 20, and then this is say 40, and then this is say 80, and this is say 120, this is 160, and say this is 200. Now, you see the numbers that we are going to present here, 4 that will come somewhere here, then 33 will be coming up to this height, then 76 will be coming up to this height, 50 is coming up to say this height, 26 is coming up to this height, 8 is coming up to this height, and 1 is this one. So, this tells the relative importance of, or you can say relative occurrence of each term in the frequency distribution. So, bar diagrams are quite useful. One may join these values. This tells us about the shape of the curve, and this is known as frequency polygon. However, if one has a classified data of the continuous variable, it is more appropriate to draw a histogram. So, for this data, one may consider, so we have say 140 to 145, 150, 155, 160, 165, 170, 175, 180, 185, 190, 195 say. So, here we have to make the scale first. We look at the values which are there 30, 35, 60 and so on. So, if we make a scale like 10, 20, 30, 40, 50, 60, 70, 80. So, the maximum value is 80. So, we may draw like this 10, 20, 30, 40, 50, 60, 70 and 80. Now, we observe the frequency for the class interval 140 to 145 is 30. So, we draw a rectangle of the height 30 in the interval 140 to 145. Then, for 145 to 150 the frequency is 35. So, we add the height up to 35 here, and for the interval 145 to 150 we consider the histogram of this length. Similarly, the next is 60. From the interval 160 to 155 to 165, it is 65. Then next it is 67. (165 to 170) is 70. 170 to 175 is 75. 175 to 80 it is 70, and 180 to 85 it is 62. 185 to 90, 190 it is 51. This tells that from 150 to 190 the distribution is almost uniform. The frequencies are almost same. They do not change too much. So, this graphical representation of the frequency distribution in a histogram form gives lot of useful information. For example, we may take the midpoints and join them using straight lines. So, this is again a frequency curve for the continuous case. We may also join them using a freehand curve, then this is known as frequency curve. So, you have frequency polygon when we join the points using straight lines. If we join using freehand, then it is frequency curve, and this is known as histogram. We also have a so called cumulative frequency curve, because once we have made the cumulative frequencies, we may plot the cumulative frequencies here in place of the ordinary frequencies. So, naturally this will be increasing based on the values here, and if we join that, this is known as relative frequency polygon or relative frequency curve, depending upon how we join them. So, the slope, or you can say the steep by which it is increasing, tells the relative importance of the each value of the variable, because that will tell how much frequency is allotted to that one. Now, when we make a histogram, then the shape of the curve tells something about that. So, for example, if we draw a histogram and the curve is coming something like, say, this, or a curve is coming like this, or a curve is coming like this, or a curve is coming like this, or a curve is coming like, etc. So, let us look at these. If we observe this type of curve, it tells that the frequency distribution is quite symmetric in nature. That means, in the beginning the values are small, then as the value increases, then the frequencies also increase, but after certain stage the frequencies again start to decrease, finally coming towards 0. This is known as bell shaped curve, which is more like a normal distribution. Or if you look at this, this is also bell shaped, but slight skew is there. So, this is moderately skewed. However, this one is heavily skewed. For example, we may consider, so this is heavily skewed distribution. Now, here it is the skew is positive, here the skew is negative. This shows that there is more than one peak of the distribution. That means, in the beginning it increases, then it decreases, then again it increases, and then again it decreases, which is showing somewhat unusual behavior. Such curves are not observed much in practice. However, if it is observed, then one should be careful. You may also have curves of this nature, that means totally increasing or totally decreasing kind of thing. For example, this shows the frequency distribution of the families with certain incomes. So, there are large number of families with very small income. There are very few families with a very high income. Then there is a middle level, that means the people of the with middle level incomes, the families with the middle level of income are also middle in number, that is moderate in number. So, this shows, this type of curve shows this type of behavior. On the other hand, this type of curve may show some sort of age distribution. For example, the persons with a, for example, in a developed country like Australia or say France, there are less number of children and the number of people who are quite old, because of the average life expectancy is high, so that number is big. So, the curve shows an increasing trend. These are somewhat unusual, but they also occur in practice. Another unusual type of distribution is something like a U-shape. U-shape curve is quite uncommon, because here it shows that in the middle the value becomes very low and in the ends the value becomes higher. But in some meteorological data where you are looking at the say cloudiness or the burstiness or say rainfall, sometimes it may happen that in the beginning there is a more rainfall and in the end there is more rainfall and in the middle there is less, or the number of places where less amount of rainfall is there or more amount of rainfall is there is more, and where moderate type of season is there, that amount or you can say number is less. So, in that case you will encounter an unusual shape curve, that is a U-shaped curve. So, you may also classify according to another characteristic, something like you may have a distribution of this nature and you may have a curve of this nature, you may have a curve of this nature. So, this tells about the concentration of the values. This is sparsely distributed, this is moderately sparsely distributed, and this is heavily concentrated distribution. Large number of values are towards the center and very few values towards the end. Here the things are more or less equally distributed. So, you can say a fat belly and a tall belly. So, this type of curves are also common. Now, by looking at the different curves, one gets a feeling about the kind of distribution that will be there. So, for example, if we observe a heavily skewed distribution, then we know the nature of the data. If we know it is symmetric, then we know the nature of the data. If it is skewed, moderately skewed or heavily skewed, we are able to make certain comments about the distribution. For example, if it is increasing or decreasing or it is a U-shape, etc. Now, next is measures. That means, from the given frequency distribution, we calculate certain measures which tell them about various characteristics of the distribution. So, the first of these are known as measures of central tendency, or you can say measures of location. Now, this is something like, see, when I have this one, we can say that most of the data is concentrated about the center. Here the center may be little bit shifted, the center may be little bit on this side, here the center may be little bit on this side of the more number of values because of the heavy weightage given to this, but there may be a long tail to the left and so on. These are known as measures of central tendency or measures of location, and there are methods of calculating that. So, here we will give example. The first one is an average. So, the easiest of the average is an arithmetic mean. An arithmetic mean, if I have the values say x1, x2, xn, is simply the 1 by n sigma xi, I is equal to 1 to n. Let us call it x bar. That means whatever observations are there, we simply take a plain average of that. This is known as arithmetic mean. This is one of the most commonly used measures of location or measures of central tendency. Now, if I have a discrete frequency distribution, that means x1, f1, x2, f2 and say xk, fk, where total is n, then the frequency distribution's average value can be calculated using the formula 1 by n sigma fi xi, where n is sigma of fi. If you have class intervals, then obviously on the left side you do not have single values of xi's. The technique used is that one takes the mid value of the class interval and calls that as xi. So, in the case of this particular example, you may take xi's as say 142.5, 147.5, 152.5, 157.5, 162.5, 167.5, 172.5, 177.5, 182.5 and 187.5. So, if these are the xi values and these are the fi values, then again we can make use of the formula sigma fi xi divided by n, where n is the total frequency here. So, this is the formula for the arithmetic mean. I must comment here that arithmetic mean is one of the most commonly used measures of central tendency. It is because of ease of calculation and also certain mathematical properties which it satisfies. For example, if I look at say each value is shifted by, suppose in place of xi the values are shifted by a, then what will happen to your average value? X bar. So, x bar will become, let me look at this formula 1 by n sigma fi xi plus a. That means the mean of this, which is also called am. Okay. So, this is equal to 1 by n sigma fi xi plus sigma fi a. Now, sigma fi is n, so this n cancels out and you are left with x bar plus a. That means, if each observation is shifted by a certain value, then the mean is also shifted by that value. Now, this is actually giving a very nice method of calculation, because many times we are dealing with either very large or very small values. So, we may shift all the values by a certain number to put them into a, for example, if you look at these values, now these values are quite inconvenient, like 142.5, 147.5 and so on. What we can do is, suppose we shift all the values by say 162.5, then this will be minus 20, this value will be minus 25, minus 30, this will be minus 15, minus 10, minus 5, 0, 5, 10, 15, 20, 25. So, and moreover, now if you see here I have shifted a as by taking minus 162.5. So, whatever average of this would have come, actually it will come x bar minus 162.5. Now, using this the calculations are much simpler, because these numbers are quite nice round numbers, multiples of 5. So, I can multiply and add. Another thing what has happened is that many minus values are coming. So, plus and minus values will cancel out each other and the total sum will become much smaller number. So, x bar can be calculated quite easily, and then in that one you just add 162.5. Sometimes we may scale also. For example, I may shift xi by say axi plus b. In that case, your arithmetic mean will become 1 by n sigma fi axi plus b. This even if we expand, then I get sigma x bar plus b. Now, in the example of the heights, suppose I take say b is equal to 162.5 and a is equal to say I put 1 by 5. Then the numbers are minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. Now you see the calculations will become extremely simple. If I calculate, suppose I call this yi's and I make a table fiyi, then you see here the calculations minus 120. So the numbers can be handled very quickly. 105, then we have minus 120, we have minus 65, we have 0, we have 70, we have 150, we have 210, and we have 62 into 4, that is 248, and then 51 into 5, that is 255. And not only that, there are minus values and there are positive values. So, if you add, many of the values will automatically get adjusted and this total will become much smaller number. So, then in the answer, what you do, if this is equal to y bar, then x bar is equal to y bar minus b by a. So, whatever answer is coming, we subtract b there and we divide by a, and the arithmetic mean of the original sequence will come. Some other useful properties that the arithmetic mean satisfies. Suppose I have two sequences of numbers. Suppose I say x1, x2, xn, and say another sequence is say y1, y2, y. So, let me put here say m numbers and here I put n numbers. So, I can calculate the means of these sequences. This is x bar, that is 1 by m sigma xi. This is y bar, say 1 by n sigma yi. So, if I am looking at the grand mean, I can consider it as m x bar plus n y bar divided by m plus n. That is the grand mean of both the sequences taken together. Because m x bar gives the total sum of the first set of values and n y bar gives you the total sum of the second set of values. So, if we add and then divide by the total number, we get. So, this arithmetic mean measure is amenable to various kind of manipulations, and that is why it is quite useful. However, it has one drawback. Suppose I consider three numbers 1, 2 and 3. What is the arithmetic mean? 1 plus 2 plus 3 is 6. 6 divided by 3 is 2. However, if I have 1, 2, 3 and another number is say minus 6, what will happen? The sum is 0 and therefore, the arithmetic mean will turn out to be 0. Now, if you are looking at this sequence minus 6, 1, 2 and 3, then actually 0 is not occurring anywhere, and in fact, 0 is less than 3 of the values. So, in some sense, it is affected by the extreme values. For example, in place of 1, 2 and minus 6, 1, 2, 3 and minus 6, I put say 10. Then the arithmetic mean will become 4, which is again bigger than these three values and less than this one, much less than this. So, it gives undue weightage to very high or very low values. So, this is one drawback of this arithmetic mean. So, there are certain measures which are used here. For example, when arithmetic means are used for evaluation, such as in a boxing competition of Olympic. So, there are 10 judges who are evaluating at the end of each round, they give certain marks, say out of 10. What the committee will do, they will discard the top value and the lowest value, and then take the average of the remaining. This is known as trimmed mean. Trimmed mean. Another option is that the highest and the lowest values are brought to the next lowest or next highest. For example, if the values are, say, suppose I write 5 values. So, 5 values are 1.1, 1.2 and say 1, and another value is say 2 and one value is say 0. Then I convert this 0 also to 1.1 and this 0 to 1. So, I will write the lowest value is 1. So, below that this is 0. So, I will convert this as 1. So, 1, 1, 1.1, 1.2 and this 2 I bring down to the next value, that is 1.2, and then take the average. This is known as Winsorized mean. So, these trimmed mean and the Winsorized means, they neutralize the effect of the extreme values, and many times in practice they are used, especially when we are judging the people based on the averages, etc. Because when there is a several judges are there who are evaluating a person, then there may be some bias in the form of certain prejudices, and to discard that thing we will avoid using the extreme values. And so, either we can totally discard them or we normalize them. So, in place of 1 we may take 2 or 3 depending upon the situation, because suppose there are in place of 10 there are 100 judges, and in that case there may be a larger number which may have to be trimmed or Winsorized. Some other quite useful measures of location are median. Now, median by the name, it means it is the middle value of the observations. For example, if I have written the sample as 1, 1.1 and 1.2, so this is the middle value. In place, suppose I have an even number, then the middle two values take the average. So, what we do, we can order the values x1 less than or equal to x2 less than or equal to say xn plus xn minus 1 less than or equal to xn. So, any sample of n values, you order them and look at the middle. That means, if it is an even number, then it will be x n plus 1 by 2 value, or it will be x n by 2 plus x n by 2 plus 1 value divided by 2. So, if n is odd and this is if n is even. So, when we have a raw data, we can order them in a sequence and find out the median using this technique. However, if I have a frequency distribution, then one may consider the following. It is written as mi is equal to xl plus n by 2 minus n l divided by f naught into c. So, what we do, we firstly consider the total frequency, that is n, and we consider up to which class it is coming, that is n by 2 where it is coming. So, we look at the cumulative frequency table. So, let me explain it through some example. So, we look at one example here. The frequency distribution is given in this form: 144.55 to 149.55, 149.55 to 154.55, 154.55 to 159.55, 159.55 to 164.55, 164.55 to 169.55, 169.55 to 174.55, 174.55 to 179.55, 179.55 to 184.55. The corresponding frequencies are 1, 3, 24, 58, 60, 27, 2 and 2. The total frequencies is 177. So, what we do? We calculate the cumulative frequencies, that is 1, 4, 28, 86, 146, 173, 175, 177. So, we look at what is 177 by 2, that is n by 2, that is 88.5. So, the value for which 86 is here, so 88.5 is above this. So, this is called the median class. Now, XL value is the lower value or the lower limit of the median class. So, in this formula median will be 164.55 plus n by 2, that is 88.5 minus NL. NL is the cumulative frequency which is occurring just before that. So, that is 86 divided by F naught. F naught is the frequency of the median class, that is 60 multiplied by C. C is the length of the class interval. So, you can see here the median value for a frequency classified data is given by XL plus n by 2 minus NL divided by F naught into C. How this is determined is by firstly looking at what is n by 2. N is the total frequency, find out what is n by 2. In the cumulative frequency table, you observe that this n by 2 where it will occur. So, since 86 is coming here, 88.5 is above this. So, that means that particular frequency is occurring in the next class, that is from 164.55 to 169.55. So, this is known as the median class. Now, when we classify the median class, then XL denotes the lower limit of that class, NL denotes the cumulative frequency just before that class, F naught is the actual frequency of that class and C is the length of the class interval. So, once we substitute these values, this value turns out to be 164.758 centimeters. Naturally, this means this is an approximate value of the median, but median will lie in this class. So, if I have the raw data, I can find out the middle value exactly, but when I have a frequency classified data, I can look at in this particular fashion. In fact, if I consider a frequency relative frequency distribution, then m value will be coming somewhere in the middle. So, that is the actually physical interpretation of the median. Another measure of central tendency is mode. Mode is that value which occurs most frequently in a given distribution. Therefore, when the raw data is given, we can actually see which value is occurring most frequently, and if we are given a histogram, we can easily point out, or if I have a frequency polygon, then I can easily make out where is the mode. For example, here this is the mode, this is the mode, or this is the mode, or in these curves this is a mode, this is a mode, this is a mode, this is a bimodal distribution, etc. So, one can find out from the shape of the distribution where is the mode likely to lie. However, once again, if I have a frequency classification data in the form of class intervals, in that case we need a particular formula. That formula is given by that mode is equal to XL plus F naught minus F of minus 1 divided by twice F naught minus F of minus 1 minus F of 1 into C. So, what we do, we consider the class interval of the maximum frequency, and F naught is the frequency of that class, that is called the modal class. F minus 1 is the frequency of the class prior to that, and F1 is the frequency after the class. XL is the lower limit of that class and C is the length of the class interval. So, this formula is used for calculating the mode when we have a frequency distribution. There is some relation between mean, median and mode. So, many times this is used, like x bar minus m naught is equal to 3 times x bar minus mi, where mi denotes the median, m naught denotes the mode, x bar denotes the arithmetic mean. So, many times this formula is also used. If we consider the frequency classified data that is given in this particular table, then you can easily see that the modal class is 164.55 to 169.5, because this is having the highest frequency. So, for this particular thing, XL is 164.5 plus 60 is the frequency of the modal class, 58 is the frequency just before that, then twice f naught minus f minus 1 minus f1, that is the frequency of the next class, into the length of the class interval. So, after simplification it turns out to be 164.836 centimeter. One drawback of the mode is that relatively one may not be able to use that, and it is it is not that convenient to calculate. That could be the thing. Some other measures of central tendency are like harmonic mean and the geometric mean. So, in the raw form, the geometric mean is defined as the product of all the values to the power 1 by n. Similarly, a harmonic mean is defined as one by sigma, that is n by 1 by xi, I is equal to 1 to n. That is the reciprocal of the arithmetic means of the reciprocals, that is called the arithmetic mean. Now, apart from the measures of central tendency, we have measures of variation or measures of dispersion or measures of variability. So, one of the popular measures of dispersion is the variance. We consider 1 by n sigma xi minus x bar whole square. Now, there are different notations for this. We may use 1 by n minus 1 here, sigma square as 1 by n sigma xi minus x bar whole square. This is known as variance, and this one is sometimes called the sample variance. Another measure is that if I consider the difference between the largest value and the smallest value, that is called the range, that is the maximum minus the minimum. We may also look at mean deviation, that is 1 by n sigma xi minus x bar, or 1 by n sigma xi minus some xm, where xm is the median. So, these are called mean deviations. All of this give information about the variability in the data. When we take sigma, that is the square root of the variance, this is known as the standard deviation. Apart from that, we have measures of skewness and kurtosis. So, that I will be telling in the next class.